Hello and welcome to Maths 8. Now, similarly to Maths 4 and to any number divisible by 4, this is going to be a recap episode. I'm going to be looking through episodes 5 to 7. So, and I'm going to be doing it in a fairly similar way to the way I did it. So let's look at intervals first of all. Okay, so intervals. So if we have open, these are intervals on the real line. So we have an open interval. This is where the endpoints are excluded. We use brackets, like so. This is open interval. Endpoints excluded. If we're going to have a closed interval, we're going to use square brackets. Closed interval. Endpoints included. So, for instance, we can say for a closed interval, we might be looking at, perhaps we're looking at an inequality such as less than equal to or greater than or equal to. And then for an open interval, we might be looking at less than or greater than, because we're going to be excluding the endpoints. Okay. So let's do 9 interval types. Okay, so let's just go through these. So yeah, let's just do these very quickly actually. So the open, and we're dealing with variables. Actually, in 7 we did say that A, B, and C tend to be constants. So yeah, so we're looking at constants. Let's look at the constants A, B. Let's be a bit more specific now that we move on a bit. So if we have a line like this, okay, and then we're going to be excluding these points here, A and B. And I'm just not going to actually label, well, I am going to label them. I just want to label them. Okay, so we can do half open. And obviously this is just, so we do A, B. So we can see we've got the open on the left. So it's going to be open, excluded on the left. And then closed, included on the right, as indicated by the square bracket. Okay, similarly we've got half closed. So we'll do it closed, included on the left. Open, excluded on the right. Okay, and then we're going to have a closed interval. So this will be both points are included. So, well, that was not supposed to be like that. But now it is. Okay, so these are both going to be closed and included there. Okay, well, okay. So then we're going to have an unbounded. Here's what I did actually. Yeah. Yeah. Okay. Let's. All right. So we've got an unbounded. So think about unbounded intervals. So these are all bounded intervals. Probably should have put that before, but well. There's a bounded interval there. So unbounded is perhaps when we're dealing with infinity. So for infinity, we could say that the interval is unbounded. So we're going to just select the whole line and just have arrows going off to the side. And that will be, obviously it's going to have to be an open interval because it's not bounded. So if it's not bounded, it's open and free. So that's what that would be. Unbounded minus infinity to infinity. But of course, so we could perhaps say that's going there, and then perhaps do something like this. So, and then we could put, so we have a closed on the left, so that's going to be included, and then we're going to go up to infinity, and that's obviously going to have to be unbounded and open. So, yeah. So let's just do A and B again. Well, we can't do A and B because it's unbounded. All right, so A is included, and everything to the right of this line is included. Okay, but what if we want to bound it on the, if we want to unbound it on the left-hand side? So we'll unbound it. We're going to use the open, so we're going to exclude that, and we're going to do from infinity again. So this time we're going to exclude A and just have everything going on that. Then the next one is going to be minus infinity. Of course, it's unbounded, and then we'll close it off at B, so include it. So from there, we're going to do B there, which I should put B there actually. Even if it's not, even if it's not always, as long as there's a dot there, I suppose it's going to be indicate well enough. So this whole area is included all the way to the left. And then, as you might imagine, we're going to do the same sort of thing that we did before, and just do it open. So yeah, so there we go. There's the open interval with B excluded there, and that is 9. So yeah, so there's that. So let's just, I might even have a bit of room to do some examples here actually. Not much room, but I've got a little bit. So if we're going to have, so if we have, say, Z is greater than 20. Okay, so we know that we can't include, so we're looking for Z, we're looking for values of Z basically. And what's the size, what's the range of that going to be as you know, these numbers change? Well, we're going to have to have an open interval on the left. So that's going to be 20. So it's going to be, so basically 20.000 recurring and then 1, if that was possible. And then we'll have to do another open interval on the right because it's going to have to be up to infinity, which of course you can't get to. So now if we're going to have, say we have Z is going to be Z can be less than, say, 10 and greater than 5. Okay, so in this case we're going to do a similar sort of thing and have, so it can be from 5 to 10 open interval and excluding both 5 and 10. Then we could do let's try so Z can be, let's do this. So what can Z be? Z can be greater than -2, and it can be let's try that maybe. Z less than or equal to 10 greater than -2. So what would that be? So I've done that kind of wrong, haven't I? Well, we're going to need to use a closed boundary. So what's the lowest value of z that we can have? It's going to be -2, including -2. It can go up to 10. So that should be okay. So yeah, it's greater than -2. It's less than or equal to 10, but including both of them. So closed interval there. And yeah, so you notice if we explicitly put two numbers in there, yeah, you're not going to have to deal with infinity, I guess. And yeah, so I think that's. I mean, yeah, I'm not really sure what else I can do on that. I suppose. Yeah, so if z is, I could do this one. Z is less than. Z is less than 5, maybe. So we're going to start at negative infinity, and we're going to go to 5, and that's going to be an open boundary. So yeah, I mean, yeah, that's the sort of stuff with intervals. And what else can we talk about? Well, let's talk about absolute values. Okay, so absolute values. So in general, so the absolute value of x is going to be x if x is greater than 0 is going to be 0 if x equals 0. It's going to be negative x if x is less than 0. So yeah. So if we're speaking about and also let's just put down all this stuff here. So the distance, say from P to Q, is going to be the absolute value of B minus A. It's going to be the absolute value of A minus B. So it just finds out the distance from between two different points. So yeah. So if we were imagining what's the distance between 5 and 8, perhaps, we could say yeah, we could do B minus A first. Let's do B minus A first and then A minus B. So it's going to be the absolute value of B minus A, which is going to be 8 minus 5. It's going to be the absolute value of 3, which is going to be 3. If we then do A minus B, we're going to see that it's going to be the absolute value of 5 minus 8. So that's going to be the absolute value of minus 3, and it equals 3 using this negative x if x is less than 0. So yeah, so it's at this stage here that we're using this this table here. And let's just do a negative one. Do a negative. Let's do a -3, 5. Let's try that one. So again, we'll do B minus A. So we're going to do 5 minus. We're going to do the absolute value of 5 minus -3. So it's going to be 5 plus 3, which is going to be the absolute value of 8, which is going to be 8. And here we're going to do the absolute value of A minus B, so it's going to be -3, absolute value of -3 minus 5. It's going to be the absolute value of -8, which again is 8. And just one more for good measure. We're going to do, yeah, let's just do two negatives then. So the distance between, say, -10, -3. Okay. So again, we'll do B minus A first. So we'll do -3 minus minus 10. So it's going to be minus 3 plus 10. So it's going to be the absolute value of 7. It's going to be 7. And similarly, if we do a minus b, we're going to do minus 10 minus 3, the absolute value of minus 10 minus 3, which is going to be minus 10 plus 3, which is going to be the absolute value of, it's going to be the absolute value of minus 10 plus 3, which is going to be the absolute value of minus 7, which again is equal to 7. Okay, now let's move on. And the next thing to look at is how we can convert real numbers to decimal. Okay. So the important thing to remember here is that when we're dealing with rational numbers, this is rationals of repeating decimals. Yeah. And irrationals do not have repeating decimals. Okay. So let's do, so if we say, yeah, let's do let's try 5/12. What might that be then? Okay. So we'll do 12 into 5. We can't do it. So then we're going to do 12 into 50, which is going to go 4 times. That didn't go too well. And we're going to subtract the 48 down here. And we're going to be left with 2. Then we're going to bring the naught down. And we're going to do 12 into 20. It's going to go 1 time. And we're going to put that down here. Subtract the 12. We're going to get 8. So then we're going to get the next 0. Put that down. So we're going to do 12 into 80, which is going to go 6 times. And we're going to get 72. And then you can see, but yeah. So the answer is going to be the same again, isn't it? Because this is going to go to 8, and then the zeros are going to keep coming down. So this is going to be recurring 6 here. So that's, I mean, that's basically how that would be done. Yeah, it's just interesting. It's 0.83 away from 5. 0.83 recurring away from 5. From 0.5. But anyway. So yeah, there's obviously a lot you can do with that. Yeah. So the next thing, okay, what should I move on to now? Okay, so yeah, I think what I'm going to do actually is I'm going to slightly change the order that I did things previously. So yeah, I'm going to talk about some of these verifications that I did. I'll speak about that at the end of this video, I think. So we spoke about what numbers as language. Well, the best start. All right. So essentially, what we're dealing with numbers, we deal with numbers, sets, and functions. So they're what we're dealing with. And a variable can be changed to anything. It will still mean exactly the same thing. That's the difference between a regular language. So 5x, 5y, 5z, 5box, all equivalent. Okay, so there's many different things we've got. We've got addition, we've got subtraction or negation there. We have multiplication, division. It's be integer division here, and radicals. Various different groupings. To isolate various terms and factors away from each other. So we also have inequality operators here. Okay, so yeah, and once more, this is a key point: is terms, things to be added, and factors, things to be multiplied. Okay. Yeah. So. Okay. So we've got equals sign. There's the equals there. And it could be equals or equivalent to. And we've also got approximately equal to here. So it'll be approximately equal to. So it's the curly equal sign. So we could perhaps say pi is approximately equal to 3.14. Yeah, it doesn't specify if you like truncate it or you round it up, which are two different ways of doing things. Truncation, yeah, rounding up is probably the way to go. So yeah, and then we have the implication stuff. I'm going to speak about that in a moment, actually. What I want to speak about here, though, is I want to say that in general, early letters in the alphabet, these are constants. Mid letters in the alphabet, these are integers, and the late letters in the alphabet, they're going to be variables. And that's the way it goes, really, and that's a good rule of thumb there. Okay, so yeah, okay, and then I made this. We had noun, pronoun, and verb. So noun is going to be number expressions. So anything that can be reduced to a number, say 3 squared, 5 plus 12, 3 times 4 plus 3, etc. So anything can be reduced to a number without additional operations is a number expression. Then a pronoun, it describes the number expression without explicitly stating it, is going to be a variable expression. So this is the equation before it's been done. So variable expression, yeah. So, well, in fact, it's not even the equation. It's simply the fragment, I suppose you could put, and then you could put it into terms or factors, depending on if you're dealing with things that to be added, like so you could say 5 plus 12. You could put that as a so you could say that the 5 plus 12 here is going to be a bit ambiguous, but you could say the 5 plus 12 is added, so it's going to be a term, and then you could say the 3x is multiplied, so it's a factor. So even so the term is an even smaller fragment, but these are still fragments before, and they're not even part of the equation. So that's a good way to look at it. And then the verb is simply well, the main verb is the equal sign. And that's how we get to doing equations. Yeah. So yeah. So equation is a declarative sentence, and the verb is equals. Well, it's not really a verb, is it? But for all intents and purposes, it is. Okay, so and then I very briefly touched upon the fact that you've got theorem, corollary, lemma, and in terms of like fact rank, maybe is a way to look at it. You could say that's 1, 2, and 3. So they're all facts, but theorem is the one. Corollary second, lemma's third place in terms of importance. Okay, so what did I actually say on implications? I didn't go into it in too much detail, did I? No, I don't think I did. No. Okay, so yeah. So basically, there's two types of implication. Only two types. All right. Implication here. So this is one way. This is one-way street. This is implies. It's if ... then. It's a one-way street. Okay, so it's and then I used I used if A and B are odd, then only going one way here, only one way, then A plus B is even. And we also say, I suppose we could say if if A was odd and B was even, then the addition would be odd. But I probably don't want to say that because there's probably no case, because unfortunately there's no case where let's stick with this one. Okay, so yeah, so this is a one-way street. So so to be explicit about it, so so A and B, it doesn't go back. So we just say, because we say A plus B is even, so we cannot go go in the opposite direction. A plus B being even does not imply. Well, I'm almost at the bottom of the page, aren't I? I'm going to have to make this bigger for next time, I think. So A plus B even does not imply that A does not imply A and B are odd. Okay. So there are some couple of two-way. There was actually one piece that I didn't actually mention. I wanted to bring in here, so I'm just going to. There's basically two small things to do left. So let's just divide out the page here at the bottom like that. And that was this issue of if we say that is essentially that 4.99999 is the same as 5.00000. And we could verify that. So we can set x to be 4.999. So then we could say just do 5. So so we could say that. Well, it's probably better to use a factor of 10, isn't it? Let's just do 10. 49.999999. Then we can say 9x is 45. X is 5. Okay. And this is also yeah, it's interesting. I think this is only one way though. I think you possibly could go back. Perhaps it would be difficult to go back. Maybe I don't think you can go back. That's the funny thing about this proof. It's verification. All right. So then the very final thing that I was going to go on is the two-way implication, which is obviously equivalent. A two-way implication is double if and only if. So it's an if and only if. And equivalent to equivalent to. Okay, so yeah, and the example I had was x plus a equals b, so we subtract a from both sides. We've got x equals b minus a, and we could say that these two statements, statement 1 here and statement 2 here, there's a double-headed arrow between them, because we can simply because we can go from, we went from this one to this one, and then if we add the a again, we're going to go x plus a, and then we get to b. So then we went from this one to this one. So you can see that the arrow, got this arrow, you've got this arrow, which makes it a double arrow. So that is going to be the end of Maths 8, end of this recap. Going to be moving on to more stuff, of course, episode 9. And of course, point out that the next recap will, of course, be in Maths 12. So until then, thanks for watching.